If you didn't get anything, you please stop me right away and I will answer your concerns. So let me go ahead and start the session for today, which is, as I have told you, related to the work. The only difference that you will see in today's session is, as I have told you, that previously you have only worked with the kinematics, sorry, which is related to the motion, which is displacement, velocity, acceleration. Today, we are going to work together with motion and the forces. So that would come under kinetics. Okay. That's the major difference. What we are going to see today, we'll see work and force, we'll discuss work and energy, we'll discuss conservation of energy. There are few more concepts, but we will not consider it. That is only there because it was mentioned in the chapter, but we are not going to talk about power and efficiency. This is not included. That we'll not discuss today. So before we go forward, we need to first discuss the idea of work done, or the idea of work done by the force. So again, I remember that this concept is generally a higher physics level concept, and maybe you have seen it already in your previous schooling or in your previous courses. However, we'll discuss it more practically and we'll discuss it through the vectorial notations, right? In order to understand, students, the work done, the definition is provided here. This is the definition. It says that a force F does work on a particle when it undergoes a displacement in the direction of the force. So for example, if the particle is here, for example, this is S1 location, the particle is going to move at location S2, and think of that the force also act on the particle. This is the force acting on the particle. So if particle P has a force acting on it and it is covering the distance, or it is displacing from S1 to S2 position under the influence of force, then we can say that the work is performed on the particle. Okay, this is what is mentioned in this definition. A force F does work on the particle when it undergoes a displacement in the direction of the force. How we make it more versatile when it comes to the curved path. So in the curved path, you think that the particle is moving with this distance, right? This is the path this is moving into. And if I show you, for example, the particle is here, let me erase it. So particle P is present here, and this particle P is moving along the path S. Okay, this is the path S, which is shown there. If I go ahead and if I go for the very small displacement referred as ds, and think of that the force is acting in this direction, this is the force, how it is acting on the particle. Just to make it more versatile, we didn't put the force in the direction of the path itself, so that I can involve the angle later on. So the force F, external force F, is acting on the particle like that, and the particle is moving along the path like this, right? So this is the scenario. And if you go further and if you see, so if I want to go for a very small patch, or if I want to go for very small distance, I will consider it as a ds, and the vectorial notation is dr. You know that how we do this thing, we say that the initial position is with a position vector r, and then at the next instant, for example, if t is equal to 0, this is the position vector. If t is equal to +1, for example, this is the second position vector, and the change in position vector is representing the vectorial form of displacement. Distance is ds here, which is the scalar part. So the distance is traveled here, the distance is shown here, force is acting like this, and the angle between these two is referred as theta, right? So if you carefully analyze this scenario, students, the displacement, as I told you, the vectorial displacement from the which is in technically the difference between these two position vectors would be referred as like this. So dr is technically the r dash minus r. And again, you can do one thing, you can use head to tail rule here to see that how can you get the value of dr. What two vectors are being added? If you use head to tail rule, r dash is equal to dr plus r, right? This is the initial configuration. R and dr, these two are being added to form the third one, which is r dash. And if you rewrite, then the displacement will be written as r dash minus r, right? Which is here. So this is one thing. Then students, one other important stuff, you will see that here we are talking about the displacement in the direction of force. So work done, when I'm going to calculate, this work done can only be utilized, it can also it can only be calculated by utilizing the force that is in the direction of displacement. So there is a reason why force was placed like this in the initial configuration, so that you can decompose it. You can make one component like this, and you can make one component like this. Now, which one is cos component and which one is sine component? This component should be which one, and this component should be which one? The one that is in the direction of dr should be which one? Which component? Cos component or sine component? The one which is here. What should I write for this force component, please?
Cosine.
So this is cosine component, right? This is f cos theta, and the one which is here, this is f sine theta, right? And so that's why the force was placed at an angle, so that you can see that you can decompose it and you can rewrite it. So if I want to calculate the work done that is performed by this force, which is in the direction of this distance ds, for the very small differential element, it would look like this. Generally in the book, u is referred for the work done, right? So du is equal to the force component, which is in the direction, into the distance involved. So ds is the small differential distance involved that was covered by the particle, and the force in that case would be f cos theta. Students, can you see, do you realize that I can rewrite this term like this? Based on your previous understanding or the concepts that you have taken in statics, do you see that I can rewrite this term here like this in the form of vectors? Can I do that? Why I'm doing it, by the way? Any idea? No idea? If there are two vectors, A and B, and if there is angle present, you have taken in statics, how do you calculate this?
Dot product.
This is the dot product, yes. So you know that you say that A dot B is equal to A magnitude, B magnitude, and cos of the angle between them, right? So if you carefully see, you have the same thing here. This term is already here, right? The magnitude of force vector cos theta is also present, and the magnitude of displacement, which is distance ds, right? When you write it in the vectorial form, it should be taken as displacement dr. So the two vectors you are dealing is a force vector and the displacement vector. That is going to give you this part, which is here as a dot product. So if you look at the dot product formulation, you know that this term which you have here is equivalent to the dot product of two vectors, that is a force vector and that is the displacement vector, right? So you can say that the work done, which is performed by a small instant or a differential element, is equal to this part. Now this is happening here for the small patch. If you want to extend it for a bigger path, so now I am going to make it for a bigger path. I say that the particle starts moving from this location and it goes like this to another location. So there are many small patches involved like that, right? When you have many small differential elements involved, how you take the total uh, the total work done in this case. How can we take the total work done in this case? We know that for a small differential element, the work done on the differential element is like this. But if the path is bigger, starting from here, going somewhere here, so there would be many of these small differential elements involved, right? And many of these small differential elements will be performing the work done that you need to take summation later on. So mathematically, when you take summation, how you do it? You take the derivative, like you do differentiation or you do integration. Yes, students.
Integration.
So to have the work done for the total path involved, when you are magnifying it from the differential side, you are taking it to the total work done involved from 1 to 2 region, then this is the same. This is the same thing what you have already discussed for the differential element, but then you need to apply the relevant limit. So it means that you are going to integrate that function, right? When you take the integration on this small differential work done, that will turn into the total work done involved from 1 to 2 location, right? So this is what is mentioned here. If you want to calculate the force or the work done by the force, and it involves certain distance, so you translate it in the form of limits, and then you use these f dot a dr displacement vector, or you use the magnitude version of them, f cos theta into ds, and use the limit relevant to whatever you are doing, right? So if f is expressed as a function of position, sometimes students, what happen that the problems comes in a way where this function is the force is provided as a function of a distance. So if you have a force which is as a distance function, then you can solve it under the integral. But there is another possibility that this f can be a constant value. If that f is a constant value, then the graph is something like this, that you have the constant value of graph of the force here on this one, right? This is the constant value. This is S1, S2. So mathematically or graphically, if you look at that, what is happening between the force and displacement, if it is a function, then the function will look like this. And when we want to perform the work done or calculate the work done, you know that integration means that you are going to take area under the curve, right? So the meaning of this thing is that you are going to perform or calculate the work done mathematically or graphically like this. If the force is constant and it's not a function of displacement, for example, then it would reduce to a simplified case, which that will look like this, where the force value is constant and only S value is changing. And technically speaking, what you can do, you can take you can take this term out of integral, right? So it will look like something like this. F, if it's a constant value of force, right? I'm talking about the scenario where it is constant. It was S1, S2, ds. And then when you further solve it, it would translate like this. So this would be the formula if you are dealing with a constant force. And if you are dealing with a force as a function of displacement, then this is the formula, right? So you need to carefully see that how you need to calculate the work done under the influence of certain force. Force can be a function itself, or it could be a constant value. And then you will use the relevant mathematical formula. Are we fine till here, students? Are we fine? Any ambiguity, any question related to what we have discussed so far?
No, thank you.
Okay, so then we go ahead, we discuss some more components that how can we calculate the work done involved if certain other type of components come into the picture. And the most important thing after the force, external force, work done by the external force, the second important thing is the work done of a weight, right? Because most of the problems, you know that mass is provided to you. If mass is provided to you, right, so you need to take into account the weight. And in most of the problem solving, you will see that weight will be performing some sort of work done. So we need to look into that how can we calculate the work done performed by the weight of the particle. Here again, I am going to uh, say that, for example, consider that a particle is moving up along the path S from S1 to S2 position. So again, the particle is moving along this path S from the initial position, which is S1, to the final position S2, right? And the particle is shown here. So initial position is here. When it is at position 1, S1 distance, the height wise distance is Y1. And when it moved to the location S2, the height wise coordinate is Y2, right? And if I want to develop a formulation, again, I need to go the same way. I need to first look at the particle. I need to look at the displacement involved. So that I can execute the formula. The formula I know that is this, that it is the dot product of a force vector and the displacement vector. So in this case, I need to first build the displacement vector dr, for example, in this case. This is, if you know that position vector, if I'm talking about a position vector, how do I write position vector? If I know the coordinates, students, what should I write for a position vector? So for example, R1, how can I rewrite it, or R2 or any position vector? How do I write it? Seems you forgot all the statics we took. This is the position vector, right? And if you are considering the, so think of this is the initial one, X1, Y1, Z1. Think of that there is a final position, which is like X2, Y2J plus Z2K. And when you take the R, which is the R2 minus Ri, this is equal to X2 minus X1I, Y2 minus Y1J, Z2 minus Z1K, right? So technically speaking, I can calculate the small uh, differential displacement by using the same formulation, the one I have shown you now. But instead of writing x2 minus x1, I will write dx. And writing instead of y2 minus y1, I will write dy. And similarly, the change in the z will be referred as dz, right? So utilizing the position vector framework, I can build what is the value of dr in this case, right? Which is equal to this one, as I have shown you. What external force is involved here? External force is, the only external force acting here is the weight itself. So students, if weight is acting downward, right, and think of that this is y-axis, which is dealing in the weight. So how can I write the vector for the weight? How can I represent vectorial form of a vector? For this, how should I write? This vector, which is W as a force, what should I write as I, J, and K? What are these values? Yes, please tell me.
0I
Okay. 0I
minus WJ
minus WJ
plus 0K.
plus 0K. So you can see this thing that this weight is only acting in y-axis, which means that x and z are 0, right? So these two components will be 0. And this is acting downward. The actual configuration of y is positive upward, so downward should be negative. So that's why you will keep only minus wj, which is mentioned here. This is the vectorial form of the weight. So after that, we know the formula. I know that the work done can be calculated by using this formula. I know that force in this case is equal to minus Wj, and I know the value of dr is equal to this vector, which is the change in x I plus change in y plus change in zk. So students, dot product of these two, how we get only this? Who will explain this thing? That when we are taking dot product of these two vectors, weight vector and the displacement vector, how it reduced into this minus w dy? How the dot product reduced to one term?
By
By the
multiplying.
by multiplying.
Is the dx and dz 0?
Okay. So dx into 0, right? Plus minus plus dy into minus w, right? And plus dz into 0, right? You know that how you open the dot product. So if you remember the statics part, when you were opening the dot product, I told you that there will be 9 different terms, right? But 6 of the terms, they become 0, because when you are dealing with I dot j, j dot k, for example, the angle is 90. So that will make it 0. But when you are dealing with I dot I, that is cos 0, which is only 3 terms will stay. I dot I, j dot j, and k dot k. These 3 terms will stay. But in this case, the vector, weight vector has zeros there. So this will reduce to 0. This will reduce to 0. Only this will stay. The middle term will stay. Out of 3, only 1 will stay. 2 will be 0. So this dot product, when you solve, it will reduce to this, and eventually it would be looking like this, that it would be weight into the final position, final vertical position minus initial vertical position. By default, remember this thing that you have negative in this formula, right? And negative indicates what? Negative indicates this, that the weight of the particle or the particle is moving upward, right? When the particle is moving upward, then technically the weight force is acting in the negative direction downward, but the displacement is happening in the positive direction, in the upward direction. So when, as per this formula, as per this convention, how you interpret negative? Negative means that something is going upward or the particle is moving upward. That would give you the negative weight. And if the particle is falling downward, then by default, the weight direction and the displacement direction will become same, right? As a result of this thing, what would happen? The overall work done will become positive. Or another way of looking at this thing is, students, when this object, when the particle is falling down, what would happen to y2? Y2 will be somewhere here, right? Y1 is somewhere here. So Y2 value should be less than Y1, right? So if, for example, I put tentative numbers, I say that this becomes 10, this becomes 20 when it is falling down. And if you plug the numbers here, this is 10 minus 20, which means that it will give you a negative answer. This value, Y2 minus Y1, will be negative. Negative, negative, the total answer is positive. So falling down is technically a positive work done. And if the object is moving upward, then this is the negative work done, right? As per the equation, as well. If you plug the values, you will get the negative and the positive will translate into the same stuff. Is it fine, students, this part? This is theoretical part, and we'll implement it as we proceed after that. So we are just building the case now, building the theoretical concept. And once we are done with that, then we'll go ahead with solve some of the problems. So are you okay with the concept here, students? Is it fine to go forward, or you have any question? No questions?
No, thank you.
Okay, so this is fine. Then in some problems, you will also see that the problems or the theoretical problems, they are using the concept of spring as well. The element of spring is present there, and you need to calculate somehow the work done involved by the spring. So we need to establish the formula to calculate the work done by the spring as well. We know this behavior. We know that when we are dealing with spring, if I apply force, the displacement of the spring will be linear, right? You know this thing, that if I am applying, if for example, if the spring is here and if I try to apply force, right, on this one, if the initial position is 0, when I apply the force, this s distance will be increasing as well, right? So by increasing by increasing the force, the displacement of the spring or the stretch in the spring will also increase. The relationship is mostly linear, which is represented by F is equal to, if I call it force in spring, Fs is equal to K times S. K here is the slope of this curve, right? So I told you previously as well that this is only true when the spring is linear elastic spring. Linear means that the elastic behavior is still elastic. It can go stretch up like that, and when you remove the load, it will go back to 0. So this means that this is elastic spring. It is not going into the deform plastically or permanently. It can get stretched and it can go back to its original position. That means elastic. And linear means that the relationship between force and displacement is a straight line. So that's why we're calling these springs as a linear elastic springs. However, there are possibilities by which you can also include non-linearity in the springs as well, right? So that's the higher topic here, but it's not included in currently. But remember this thing, that springs can be non-linear as well, depending on if you are dealing with the variable pitch distance or if you are dealing with the variable coil diameter, like a leaf type spring or conical springs, then it will be different. So if it's the simple scenario of the spring, like as you have seen here, this is how you represent force for in the spring. Then we go forward, students, and we look into that. For example, think of this scenario, the one you see here, right? And in the current scenario, think of that the initial stretch or initial unstretched length of the spring is still here, like spring is like this. What you did, you tried to apply the force like this. So you tried to pull that particle, and as a result of this thing, stretched happen in the spring. Okay, so when you apply the force, this is the external force Fe that you are applying, and as a result of this thing, the particle will move this way. But students, if you're stretching it, the external force is stretching the spring. What would be the direction of this of the force of the spring if you are stretching it outward? If you're stretching it outward, the external force you are applying is you are pulling the spring outward, right? But what is the spring force direction as a result of this thing? What is the force that was present in the spring, or how the spring is applying the force? So there are two
Fs
forces.
will be opposite direction.
That's true. So remember one thing, that there are two types of forces which are present in that scenario. The Fe, I call it external force. E means external. So you are pulling the force outward, particle outward. As a result, the spring is being stretched, but the force within the spring is in the opposite direction. So that's why if you see, this force is like in the opposite direction, which is the force on the particular force in the spring, Fs, right? So remember this thing that that's present there. Now, the rule is very simple. If this force, Fs, and the displacement, like the stretching of the spring, if they both are in the same direction, then this is a positive work done. And if they both are opposite, then it would be a negative work done. So I need to ask you now, you will tell me that which scenario will give you the positive work and which scenario will give you the negative work, right? So listen carefully. In the first case, when I am stretching, so initially it is present here, like this, and I start applying the force Fe. As a result, the elongation will happen like this, right? The spring will get stretched. But remember this thing that the force in the spring is always in the opposite direction. So what do you think that in this case, when you are stretching it outward, that work done should be positive or negative? When the spring is being stretched or elongated, the work done is positive or negative? Yes, students.
Negative.
And you need to explain why. Why it's negative? In case of elongation of the spring, why it's negative work?
Because
Because,
the
yes,
S is in
Opposite
opposite
direction.
direction.
that's true. Because the force in the spring and the distance S, they are both in the opposite direction. So when you are dealing with a scenario where you are elongating the spring, they both give you the negative, they are on the opposite direction. So they will give you the negative answer, right? But in the case when you are dealing with the compression, think of that it is already compressed, right? And you're trying to compress the spring. So in this case, what would be the scenario? If I erase this thing and think of the scenario that it is already stretched and now it is being compressed, for example, it is going in that direction. So in this case, what would be the work done? When it is being compressed, what would be the direction of force and what would be the direction of displacement? Yes, students.
Displacement will be negative.
No, displacement, I'm asking about the work done. Because in order to evaluate the work done, it's positive or negative, you need to see both displacement and the force in the spring should be in the same direction. So in this case, the S is also like this, right? Stretches like this, it's in compression. And the force in the spring is always pulling like that because it already was in the stretched position and now it's being going back to its original location. So in this case, if you see Fs and S both are in the same direction in case of compression of a spring. So as a result of this thing, work done on the spring is positive. So that's why I have a positive here in this equation. If you want to rewrite that equation for the elongation, then instead of negative positive, you need to go for a negative number, right? So this equation will flip or it will go like this if you are dealing with elongation. If you are dealing with compression, then this is true. This is right because the work done will be positive in this case. So this is a small tricky thing that you need to remember and you need to always see the force in the spring and the displacement happening in the spring so that you can realize that is it a positive work done or a negative work done, right? In case of compression, as a rule, remember that this is more like a positive work where both are in the same direction. So students, what I did after that, I go ahead with the same definition of work done, where I have a force and where I have a displacement, for example, both are in the same direction. So that's why cos theta is not involved this time, because the force is not an angle. Force is technically at it's the same distance location. So cos will not be involved. Okay, and Fs is the spring force, and this is the displacement involved, and these are the limits involved. So after that, I know that Fs is equal to Ks. The value, I know that if it's a linear spring, then F, S, and K are related. Basically, F is equal to Ks. I know that the force can be calculated by the spring constant and the displacement. So I plug the value of force here. When I plug the value of force here, right, now it would be Ks ds. Ks will be the value of force. And when I solve the integration now, or I solve the limit, you know that S, integral of S will become S square over 2, right? So it would be like K is, let's say, constant, and it would become S square over 2, and then you have a limit, S2 and S1, like this. Then you further solve it, and it will look like this. So when you are going to go ahead for the calculation of work done in the spring, so the equation is like this. U is equal to 1 minus 2. From 1 to 2, the work done will be first half Ks2 square. S2 is the final position, minus half Ks1, the initial position, right? So remember this thing, that this is how you can calculate the work done in the spring. And here I have given you the same idea that spring extension means that spring force and displacement are in the opposite direction. That will be work done as a negative. If both are the opposite, which is elongate, in case of elongation, it's a negative work. If it's the same direction as what you have seen here, it would be the positive work. So these are the concepts related to the calculation of work of a spring. Are we fine till here, students? Yes, students, are we okay till here?
Yes.
Okay. So there are some scenarios now that we will see, that in some different scenarios, how can we look into the work done involved? So think of a scenario where a trolley is moving, for example, on a slope with certain angle. So how can we try to solve, or how can we develop equations related to work in this case? So if this is the case, and you are supposed to analyze the work done involved by different forces, first thing is that I need to draw the free body diagram. So this is how the slope will look like, how the object will look like. The towing force which is being applied here is referred here at an angle phi, for example, right? It's trying to pull the trolley upward, and as a result, the trolley is moving. Then we call normal reaction. Normal reaction, you know, that is because of the contact of the object, right? And it is generally 90-degree on the surface. However, weight is always acting downward. Weight does not take any angle. So if this is the one, weight will always be acting downward, right? Let's say the total, if I show you, for example, the perpendicular axis to the plane where the normal reaction is working is here, whereas the weight is acting like this. Weight is acting this way. And there is an angle theta present there here. So if you are supposed to solve this question, there are two major forces which are acting in this case. So the movement is like this. S is happening here. The object is moving in this direction, S. So based on this thing, we can say that in this direction, S, which forces are in the same direction and are contributing towards the positive work done. So if I, like take the components here, that this will become T cos phi, T sin phi. And I can see here that this component of the towing force is in the same direction of S. So technically, this is providing you the work done. This component of the force is providing you the work done. And this work done should be positive number. Why it should be positive number? Because it is in the same direction of the displacement. Okay. Is there any negative work as well, which is present here by any of the force? Do you see any force which is contributing as a negative? The answer is yes. So if you see, the weight is acting like this is angle theta, right? So if you resolve into its components, there would be one component like this. For a weight, there would be one component like this. S is this way. Movement is this way. So what is this weight component, students? The one I have just mentioned. What should I write for this? Sine or cos of weight?
Sine.
Yes, this is opposite to the angle. So this should be W sine theta, and this would be W cos theta, right? Now you can analyze that this weight component and the displacement are in the opposite side. So this should be a negative. This work done should be a negative work done. So sometimes the question comes like that, where you have different type of forces acting. In fact, you will see the same three types what we have seen. External force should be present, pulling or pushing the object. Then you will see in some time that gravity is present, weight is present. So you will analyze the same way. Sometime you will see that spring is present. So in the problems, all these 3-4 types of different work done will be involved. You need to look into the work done by each one of them separately and then collectively. So for example, if I get a value of 220 here, I'm just assuming numbers when I plug the values. And let's say when I solve this, I get the value of work done, let's say 12. So sometime the question says that what is the net work done? So you will put all the positive and the negative, and then you will say that the final net work is 8, for example. So some questions they ask you these things, that what is the net work done or what is the total work done involved, which means that with respect to each force, you will solve the components, you will solve the values for each force, positive, negative, and eventually at the end, you will do the final calculation by taking it as a net work done. So this is something which is there. Now we'll go ahead and we'll practically solve one of the problems related to the same idea. So students, the question says that the 10 kg block, which is here, is resting on a smooth incline. If the spring is originally stretched 0.5 meter, okay, so initially it is stretched 0.5 here. Determine the total work done by all forces acting on the block when the horizontal force P, this is 400 on the block, pushes the block up to the plane by 2 meters. So when this force of 400 is applied and it pushed the specimen, it pushed the object up to 2 meters, you need to look into that what would be the total work done and determine the total work done by all forces. Yes, students. So what do you think? What should we do? What is needed here? First identify how many types of work done you see, different type of forces, how many work done are involved when you try to compute or solve this? Yes. How many type of different work done you see in this problem?
2.
So which two?
1 by P.
By the external force P and
Weight.
the weight of the object. Okay. So weight. But what about spring? Spring is also there, right?
Yeah, that too.
Yeah, so there are 3 different type of work done which are present here in this question. Very first thing, students, would be that you need to draw quickly a free body diagram, right? So a free body diagram, for example, if the object is on the inclined slope like this, normal reaction, N is here like this. Sorry, this should be N. The weight is acting downward like this, right? So if you extend the lines, weight is acting downward like this. And what should be the angle here with the inclination for a weight?
30.
30. Okay. Then force 400 is acting in the horizontal direction. What should be this angle? What should be this angle, students? 430, right? And what else you see? You see that when you push the 400 force for the block upward, what would be the direction of spring force? What would be the direction of spring force? When this block is being pulled upward with an external force of 400 Newton, how the force will develop in the spring? The spring will try to bring it back, right? If you are going to stretch the spring, the same scenario, the force in the spring will look like this, right? It's trying to bring it back, stretch it back to the initial position. When the external force 400 Newton is trying to pull the block upward, the force in the spring is trying to bring the object back to the initial position. So spring force will look like this. So the force 400 is here. We need to look at how it is going to provide the work done. Weight is involved here. So weight, you know, that is 10 kgs, 10 into 9.81. This will become 98.1 Newton, right? This is the weight acting downward, and the spring force is present here, right? Remember that the displacement is happening in this direction. So now based on this thing, you need to calculate the three components of work done individually first, and then you need to look at the net work done. So what should I do? With the external force P, what should I write for the work done? Force into what, sorry, students?
Distance.
Distance. Here the force is varying or the force is constant?
It's constant.
It's a constant value, right? This force, if I resolve, so for example, if you see, this is the block on the surface and 400 is like this, right? So this is 30. If you resolve it into its components, the two components will look like, there is a one component like this for the force, and there is a one component like this, right? So this component should be cos component or sine component. The one which is in the direction of S should be a 400 cos 30 or sine 30.
Sine 30.
Is it sine or cos? Say, see again. The triangle is
That's
like
cos.
this.
It's cos 30.
Yes. So
Yeah.
it is cos,
Yeah.
right? If you see. So if I write the work done now, it should be 400, right? Into cos 30. And what is the distance involved? Like if you remember, it was S2 minus S1. So S2 here is 2, the final position minus the initial position is 0.5, right? And you know that this will contribute into the positive work done or negative work done. Both force and the displacement are in the same direction or in opposite directions. Yes, students. Is it the same direction or the opposite direction?
Same.
Same.
Same. So this should be a positive number. Can you tell me the value? Please calculate and tell me what is this value.
$519.6.
519.6. Okay. Okay. Let me just quickly see. Sorry, there is one thing I think I didn't write it properly. Let me erase one thing here. This 2 is total here. Sorry. 0.5 is here. So it's not included here. 2 is separate. So your work done should be 400 cos 30 and this distance 2, right? Because it's being stretched from here to here. 0.5 is not here. I minus it. I thought it's here and that, but no, in the real problem, it's behind it. So its initial stretch is 0.5, which is not provided initially, and then the weight is this force is applied 400. So it should be the distance needs to be 2, not 2 minus 0.5. So if you look at the value, I think it is 600 something with this.
Yeah, 692.8.
692, yes. One thing happen is that if you try to draw the diagram on the same, like you have a possibility that maybe you will do mistake like this based on the distances. Some things are not clear and you can take a wrong value. So it's always recommended that you draw this diagram separately, right? You show only the object itself and then you draw the free body diagram, right? Otherwise there are chances of that some values you will misread and then it will be a problem. So this is one thing, students. Then the next thing is we are going forward for the next part. So we calculated basically based on the external force that how much would be the work done for the horizontal force P component. Now we are looking into the spring force. So in case of the spring force, again, if you look here, right? Here, for example, this is S1 and this is S2. You remember that what was our equation here for the spring? It was half Ks square minus half Ks1 square, right? The work done was like with this formula. Half Ks2 square final position square minus half Ks1 initial position square. So if you look at the second component now, what should you do? You need to write work done based on the spring is equal to half Ks2 square minus half Ks1 square. The only thing you need to see here that when we develop the equation, for us, it was the case of compression, not elongation. So compression means that the force and the distance were in the same direction. But here, what would happen, students, here? If you look at this scenario, the block will move like this. So this spring will compress or elongate. If the block moves up, what is happening to the spring? Is it compressive or is it in the elongation side?
Elongation.
So elongation means that the spring force will be like this. However, the distance traveled will be in the opposite direction, right? So when I write the equation, this is the negative work that I need to do. I need to call it a negative work done, right? So you need to realize this. S1, you know that is half, this one, 0.5. The final stretch in the distance is here. If you look back here, this is S2, S1. S1 has this much value, 0.5. S2 has the total stretch, 2.5. Right? That's why this stretch is mentioned here. The final S2 stretch is equal to 0.5 times 2. So you put the S2 value, you put the S1 value, K is already provided in the question. If you look here, the value of K is provided here in the question. It's 30 Newton per meter, which is also provided. So you can go ahead and you can execute this equation. Just look at it, just verify that if the answer here is right and the calculations are making sense to you. Yes, students, the numbers make sense here for you. The only trick here is that you need to know the right value. You need to know the right distance. So the initial position is S1 here. The final position is S2, right? The question already gave you this S1. If you take a reference from here, this is 0.5. And the total distance for S2 is 2.5. So these two distances you need to plug into the equation for the work done. And the component will look like negative 90 joule in this case. By the way, what are the units for work?
Joule.
Or it's force into distance, which means this is Newton meter, right? So you can either write Newton meter or you can write it, you can call it joule. It's referred as joule. Then students, the third part is the force because of the weight. So if you look at the force because of the weight, again, if you go back here into the scenario, you will see this thing. We know that the weight is 98.1, right? We calculated it as 10 into 9.81. This is the weight in Newton. Force, it is provided as a kg mass, but then you need to convert it into the Newton, right? So that you can use it like a force. And then the value is, again, you know that if it is moving up, so it's technically the scenario is that it's moving up. Up case, you remember we said that it would be a negative work done if the object is moving up. If the object is falling down, then this is the positive, because then the weight and the displacement direction both are in the same direction. But if the displacement is moving up, if the particle is moving upward and the weight is acting downward, then this is again the opposite direction, which means that the weight in this case should also be negative, right? So for example, in this case, if I use the equation, it was minus W delta Y. It was like this, right? And here minus W Y2 minus Y1. If it is moving upward, this value here is Y2. And if I take the initial position here, 0, Y1 is 0. So y1 is 0 and y2 is equal to 2 times sine 30. This is provided, angle is provided. So even then, if you don't know what is this is not provided, you can calculate based on the trigonometry that this will be 2 cos theta here and this will be 2 sine theta here. So it would be minus 9 point, in fact, 98.1 into 2 times sine 30, right? That would be the weight, work done due to the weight component, which is here, this one, right? And eventually it will look like it will be 98.1. Is there any work done involved because of the normal reaction? This one? Would it contribute? Yes,
No, it's not.
because it's 90° to the displacement, right? So if it is 90° to the displacement, then it is not in the direction. There is no component of this one that is in the direction of displacement. So it will not contribute in any work done related calculation. So it will show you no work related to that. And then you need to calculate the total work. So total work is the net work. So whatever is a positive value, you write down as a positive. Whatever is a negative value, you write down as a negative number. And then that's all. That's how you will calculate the net answer, right? So we have 90 as negative, 98.1 as negative because of the spring force and the weight. And from the external force for 400, you were getting this positive work. So net work is around 505. This is one of the questions where you have all of the three things we have taken. You have external force, you have the presence of spring, you also have the presence of weight. All three components are present there in the calculation of work done, right? So similar type of problems are there. I'm going to assign you one homework, hopefully by the end of this week, just for more practice. And this is something we'll do. So students, are we clear till here? Any question related to the problem, this one?
No, Professor, all clear.
Okay. Okay, so then students will go to the next part where we will see one more alternate form of the same formulation. And that formulation will give us or will take us towards the principle of work and energy, right? That will convert or that will correlate the information that how the work done and the energy is correlated. So what we do, for example, if you consider a particle P that is path measured with an inertial coordinate system. So what they do, there's a curved path here. If you see, this is position 1, position 2, and the particle is moving in this path. Here, the coordinates established are the normal and tangential components, coordinates. So if I want to take the tangential acceleration into account, because you know that this tangent acceleration is more like the normal acceleration on this curved path. If you take the normal acceleration, that would be more like the centripetal acceleration, right? But the regular acceleration that's coming as a derivative out of a derivative of the velocity, that is the tangential acceleration. I know that this acceleration is related to each other through the displacement and the velocity with this equation. This is the one of the basic equations of dynamics. And I know that I can also involve the Newton's second law here. So if I use Newton's second law, right, and I say that sum of all forces acting in the tangential axis is equal to mass times the acceleration in tangential axis. And then later on, I get the value of AT from here and I plug it here, right? So you know that this is how it will look like. V times dV over ds, right? Then later on, what I will do, I will take this ds on the other side with the force. So the left-hand side will look like this, where I'm talking about the summation of force into displacement, right, with a particular limit. And on the other hand, I have the on the right hand side, I have the mass times velocity, where I have the limits on the velocity. So if I solve this part, you know, mass is taken constant outside, and it will become v square over 2, right? So you will put the limits. So this is something like this, m v square over 2, and then you are putting the limit v2 over v1, final velocity minus initial velocity. So solving this part will give me these two terms. And on this side, if you see, this is force into distance. So we already know that this is the representation of work done on this side. So on the left hand side, you have the term which is saying sum of all work done, sum of the work done by all forces from 1 to 2 is equal to, do you remember what is this? Half mv square is what?
Kinetic energy.
This is kinetic energy. Yes. So this is the final kinetic energy at the final instant, and this is the initial kinetic energy. So if you take a difference of these two kinetic energy, that would be equal to the sum of the work done performed by the forces in the system, right? The equation turn out to like that. And this is the relationship where work done and the energy is correlated based on the speed, because this is the speed. So that's why we are calling it that we can relate forces to the speed at some points in this case. So if I rewrite the equation will look like this. This is in the book, generally kinetic energy is not written as this. Like in your conventional books, you have seen kinetic energy written like that. In the current book, it is represented with a symbol T, right? So T2, that is technically the final kinetic energy, is equal to the initial kinetic energy plus the sum of work done by all of the forces on the particle, right? So the equation or the principle will look like this. And if I explain it again, it says the particle's initial kinetic energy plus the work done by all of the forces acting on the particle as it moves from the initial to its final position is equal to the particle's final kinetic energy. So the relationship of initial and final kinetic energy with respect to the work done is established using this equation, right? We'll see now how can we use this equation and we can solve it, solve some of the problems related to that, right? Again, students, how you go ahead, you first need to draw the free body diagrams, establish the proper coordinates, free body diagram, then try to apply the equation as it's mentioned here. The value of kinetic energy is half mv square that you will use. Speeds will be provided or speeds will be given at some point, right? So this is the same thing related to how can we involve spring work done, for example, as well in this case. So it will be the same as we have established. Principle of work and energy for the system of particles. So if we have n number of particles which are present here, so principle of work and energy can be extended to include the system of n particles isolated within the enclosed region of the space. So I can extend this principle, the one that was for one particle, to the number of n particles as well, right? Where I can say that sum of kinetic energy of all particles, initial kinetic energy, plus sum of all of the work done by the external forces in the system is equal to the summation of the kinetic energy, final kinetic energy of the system as well. So it can be applied for the number of particles as well if you're dealing with more particles. In some of the problem students, you also have a concept of friction. So for example, you will see that, however, here we are dealing with the dynamic friction because you will be dealing with the dynamics, which means motion, sliding, moving of one object on the other one. So this is technically referred as dynamic friction. In dynamic friction, do you remember that? Have you seen this formula? Mu n. This is mu. Have you taken this formula before or no? In any of your course or anything?
Coefficient of friction.
Coefficient of friction, F is equal to mu n. Have you seen this thing before? Yes, students. Are you aware of this formula for friction? Are you aware of this formula or no? if the object is sliding, let's say this block is sliding on a surface, the external force P is provided, right? Is applying on the surface and the object is moving. For example, it's covered distance as shown here. When I draw the free body diagram, or by the way, if I need to say it like this, if you magnify this region, do you agree that this magnified region will look like this? Because at the magnified level, when you go into the microns or something 10 raised to power 6 dimension, you know that these surfaces are not flat. They appear flat because we are looking at them in the dimension which is macro dimension, not micro dimension. So when you go into the micro dimension, surfaces are generally having surface roughness like this. This is the roughness profile. So you have a rough profile on the one part, and if it is sliding on the other part, the same roughness is present there. And generally, the roughness, the profiles are like wavy profiles like that. So generally, there are peaks and valleys, you say that. So you have these peak and valleys on the first part, and it's moving on another part, so there are peak and valleys involved on the other one. So when this object is pulled in this direction, students, what is happening here? What would happen here? At the micro level, when the two surfaces are moving on each other, what do you think what would happen? Yes, students. Are you there or should I pick one? Any volunteer?
There's going to be a force resisting the motion.
That's true. So if you look at the surfaces here, these peak and valleys, they are kind of entangled with each other, right? So when the object is at rest, generally we call it static friction, which says that these peaks and valleys are engaged, are kind of entangled with each other. When you try to apply force, generally there is a kind of a resistance towards the motion, right? Initially, it will not move unless you break certain value of force of friction, and then it will start moving. Now, that part where it is not moving, that is called as static friction. That is generally studied under statics, but it was not the part of course learning outcome, so it was not covered there. But it is important here because when the object starts to move, even then this resistance is there, but that resistance is less. So we generally say that if the block is moving here like this with the external force, if it goes like with a movement, there's a kind of friction force present in the opposite direction as a result of this movement, right? And the relationship shows that this friction force is kind of proportional to the normal reaction. So the normal reaction that is coming from the object and the friction force, they are related, right? So if I say they both are proportional, initially I say like this, and then if I remove the constant of proportionality, that constant of proportionality is mu. That is called as coefficient of friction, right? And this coefficient of friction, it varies material to material. So it depends on that what type of two materials which are present, and it depends on these different parameters which are there. But to keep their discussion short, this is how you can calculate the friction force. If you know the value of normal reaction, and if you know that what is the value of coefficient of friction, in most of the times, the problems you will see, this will be provided to you. The value of mu will be provided, so you are just plugging the number, right? But at some points, you can, at higher level courses, you have the equipment where you can calculate this experimentally as well. Generally, in mechanics course, we have the lab where students, they use different materials, they use different inclination, and they figure out this coefficient of friction. Anyway, you got the idea, students, related to that, the coefficient of friction, or should I explain it more? The friction concept. Important thing is you need to understand that why this resistance is present in the first place. And it is present in the first place because of this surface roughness of both parts or both objects and the engagement of peaks and valleys into each other. So they are kind of entangled and fixed within each other. When you try to apply a force, external force, and try to move the object, the resistance come as a result of this thing. Okay. So this is the idea. Now, if I go back here to the discussion. So when I'm talking about work of the friction caused by sliding, one applied force P just balances the resultant frictional force, which is mu Kn. Then due to the equilibrium, a constant velocity V is maintained and the frictional force equal to P is, so this is the case of sliding, work done in the case of sliding. And the scenario is built in a way that the equilibrium is maintained, which means that the external force, the applied force F, is balancing the resulting frictional force. So this is the condition of dynamic equilibrium, where this is maintained. Now, students, if you look at this one, if I go back to the previous equation that we have built here, we're trying to apply this equation here. So I have the initial kinetic energy, final kinetic energy based on the velocities, and I will see how different external forces are acting and providing the work, right? When the object moves from one to second location. So how many forces you see in this case, in the case of sliding? How many forces are here in the system?
4.
And what are these 4 forces?
Weight, normal,
Okay,
the force P, and friction.
okay, that's fine. So generally, here in this case, if you see weight and if you see normal reaction, you know that they are 90-degree in this case of sliding. If there is no inclination, they are 90-degree to the direction of the distance. So generally they are not participating. If it's the straight surface, it will not participate. Weight will come in only play if there is an inclination involved. Then the component of weight will come and it will take part in the work done. If it is the straight case like this, then the two forces which are in the direction of displacement, it is technically the applied force and it is technically the frictional force. So this applied force into S will be a positive work done because both are in the same direction, displacement and the applied force. However, if you talk about the work done, that would be in the negative. It will give you the negative work done, right? So here it is the F into S, friction into the distance, and then friction is translated as mu K into N. So we know that F is equal to mu K N. Mu K is kinetic, coefficient of kinetic friction, because we are dealing with movement. So this value is different. Similarly, we have mu S, but that's for static friction. That's the static case. So remember that you are picking only the kinetic one when you are dealing, right? Mu Kn, but mu is two. Technically, there are two mu's. One is for the static case and the other one is for the dynamic case, right? So here we need to work with the dynamic coefficient of friction. So the equation will look something like this. It is the initial kinetic energy, the two forces which are there, external force, applied force, and the frictional force, and the final kinetic energy. Students, by the way, this is a simplified approach. If you go at the higher level courses or higher level uh, scenarios where you are dealing with the friction, you see that there would be heat generation as well because of the adhesion or the rubbing action of two surfaces with each other. The heat is also generated and the vibrations are also produced, right? So these are the other two forms of forces and energy, you can say that you need to take into account at higher level. right? When you go for the proper energy balance, the remaining part, which is not included here or assumed not taking part, they are present here, right? Generally, at higher level, this is needed. But at this level, because this is more like the initial first year level, second year level course, so you are ignoring them. So that's basically the frictional force caused by the sliding. Now, students, we solve one more problem related to the same concept. So this question says that the 17.5 kilonewton automobile, which is a car here, is traveling down the 10-degree incline road at the speed of 6 meters per second. If the driver jams on the brake, causing the wheels to lock, determine how far his tires skid on the road. What would be the distance S? When he pressed the brake, how much skidding will happen? Coefficient of kinetic friction between wheels and the roads are provided to be 0.5. Okay. Students, one major indication when you are dealing with when you see scenarios where, for example, you have work done or energy involved, you will see that the values of velocities are provided, which is kind of indication that you need to go towards this formula, the one that you have seen here, this one, right? So kinetic energy formula will be involved. That's why velocities are provided. If you go to the previous one, for example, the one you have solved here, you don't have any information about velocity and stuff like that. So that was more like traditional problem related to the work done, right? But when you go ahead and you see that the velocities are provided and somehow work and energy is in the picture, then you need to understand that technically we are dealing with the principle of work and energy, which means that we will be dealing with this equation, right? So this is just like a tip that you realize that what sort of formula needs to be used. So anyway, if we go ahead, students, here, one thing is again that normal reaction will be present. I think I already have drawn something, so I will draw it again. The normal reaction, you know, that is here. This is the normal reaction. Weight will be acting downward like this, right? So weight is going downward like this. If I draw like this, what would be this angle for the weight? If I draw the angle, what would be the angle, students? The vertical is like this, but based on the inclination, what is this angle? It's provided 10 degrees, right? 10 degrees are provided here. So weight is acting downward like this. Normal reaction is acting upward like this. Car is moving this way, right? So the friction force will be present here like this. Okay. Now, if I want to execute this scenario, right? I know the friction force which is present. I know the velocities which are present, right? It's moving with the speed of 6 meters per second here. And when you will press the brake, you know that final velocity here will become
0.
0, right? So kind of velocity information is there. So I can execute this very easily. I can execute the formula that I have seen here. I can put the velocity, mass is provided for the way automobile. So these two parts can be easily calculated. How many forces are present in the middle part here? So if you see, you will see that there is a frictional force present right here. Friction force is present here. How can I calculate friction force? Friction force is equal to mu k into n, right? I know the value of mu. Can I calculate n somehow? Normal reaction? Yes, students. If I know the value of n, I can calculate the friction force. right? And things are easy for me then in order to do the calculation. What do you think? What should I do?
So you take n as the weight, as the
Ye-
opposite of the weight.
So how you justify it, what you are doing, you can see that this side here, for example, weight is present and this side the normal reaction is present, right? So if I put x and y, x is like this as per the inclination, because this is what I'm dealing, the distance is in s direction, x direction. If I take sum of forces in y, I'm considering equilibrium in y direction. So it would be equal to, what? N positive minus weight equal to 0, or in other words, N is equal to W, right? Do I have the value of W, weight of the object? But remember,
Professor?
remember, yes, I need to put the angle, yes. I think you were mentioning this, right? Or anything else?
Yeah, the angle.
Yes. So if you put NA like this and W like this, this is W, sorry, this is W here. Let me erase it a little bit more. So this is the object here. Weight is here. And if I draw, this is the normal reaction. This angle is 10. So which component of weight is technically present in the direction of NA? Cos component or sine component? This is weight, right? I need to take the component of weight which is in the direction of NA. Which one is it? Cos or sine?
Cosine.
So it has one component like this, and it has another component like this, right? The one which is here is W cos 10. The one that is here is W sine 10, right? So when I say sum of forces in Y to be 0, it should be NA minus W cos 10 equal to 0, right? The equation will look like this. So we know the value here, we know the weight. So if I plug the weight value, what should be the value of NA, students? What would be the value of NA? Can you please calculate quickly and tell me that what is the value of NA in this case? If you do not want to deal with kilonewton, you just multiply 7.5 into 1000. So you will have a Newton value. Cos 10 of 175 into 1000. 0.5 into 1000, yes. What's the value, students?
17.2 kilonewtons.
17.2 kilonewton. Okay. Okay. So you got the value of NA from here, right? Now, how many forces you see that will come contribute into the work done? Because I need to execute this one, right? I need to know how many forces are acting in this and providing me the work done. So one is the friction force, right? I know that friction force is equal to F into mu K into N A, right? Which is equal to 0.5 times this 17.2. So I know this one. Is there any other force acting? Yes, students, is there any other force acting? Do you see any other force acting performing a work done?
The sign component of weight.
Yes, this one. This sign component of weight, this is in the direction of displacement, right? So these two forces are acting in the direction. So if I go ahead and write the big equation with everything, this is the first thing. You calculated the value, right? This is 17.2 kilonewton, and then half of it is around 0.8, right? 8.6, sorry, kilonewton. And then you executed the formula. So you executed the formula half m v square. Initial v1 is 6 provided. The second part v is 0. So this whole thing will be 0. Because velocity v2 is 0. It will, when you press the brake, it will eventually become 0. And then you have two forces contributing into the work done. So you have a weight times sine 10. This distance you do not know. So distance you will just write s minus this frictional force into s, right? So these two you do not know. You know that frictional force and the displacement are in the opposite direction. So this friction force should come with a negative answer, negative number. However, the weight here, weight and the displacement are the same direction. So that's why it will come with a positive number. So that's why you have positive here. Okay. So everything is known. The only unknown is distance s, right? That you can get out of this equation. One other thing you remember that you are executing half mv square. So this needs to be mass. What you have been given here is the weight, right? So W is equal to mg. When you want to convert it into the mass, so you divide it by g, right? That's what you have done here. You divided this thing, weight divided by 9.81, so that you can represent the mass. So students, did you get this part, this problem? Any question related to that?
No.
Anyone else? If you have any question, if you didn't get anything in the problem, I can explain again. Everything is good?
Oh, yeah. Thank you,
Yes, it's
Professor.
clear, Professor.
Okay. So students, now we have taken this theoretical part. We have solved two problems. I have one more problem, but I will leave it with you. So this question is there. Try to solve this thing at your own. Try to understand this thing at your own. And in case if you feel troubled, then I can come back next time and I can try to work on this thing with you, right? But try to solve this third problem at your own. And I will also assign one homework, 2-3 problems related to this lecture, 2-3 problems related to what I'm going to deliver in the next session, which is Thursday, right? This way we'll finalize the dynamics part. So I think previously we have 4 sessions. This is kind of 5th session. The next session, which is on the linear impulse and momentum. So we'll cover that part, and that will finalize our dynamics part. I will give you announcement for the quiz and for the exam as well. Okay, that would be right after it. So I think that's all for today. That's all from my side. If you have any questions, go ahead. Otherwise, we are fine for the day. Yes,
Professor, do you take attendance?
I am going to take a screenshot now. So just give me a moment. Just give me a minute. I'll take a screenshot quickly. Okay. So students, I have taken the screenshot. It's fine from my side. If you have question, go ahead. I can explain again. Otherwise, we are fine for the day.
Professor,
Yes.
are you fine with postponing the homework for like a couple more days, like till Thursday?
When was it due?
Today at midnight.
Okay, I can make it till Thursday then.
Okay, Thursday midnight?
Yes, yes.
All right. Thank you, Professor.
Okay then. Okay, take care, students. Good luck. Bye.